So you'll see the scheduling presentation itself. There's going to be a PBS script file that's going to contain all the information on how to submit jobs in a table format. There's a scheduler commands about all the different scheduler commands and how their output looks like, as well as an online scheduling worksheet. These are the problems that we're going to be going through the next 3 days. Mostly about submitting jobs and looking at them. So they're all available in this directory here.
No.
You could also grab the answers to all the questions, as well as all the prerequisite stuff you need to run some of the more complex questions. So in this first beginning, we're going to go through scheduling theory, some basic job submission, and submitting parallel computing jobs. A little bit about batch scheduling. Batch scheduling is not used when you need a service, for example, a web server that runs all the time. It's preferred when you have one or more job simulations that need to run and you wish to get the results back. So basically, what you want is, if you have a simulation, you need to run the simulation, and you want to get an answer for the result, this is where you use batch scheduling. If you would like to have a web server, then that's more of a cloud type information. You don't want to use a batch scheduler for that type of
Okay.
the advantage of using batch scheduling is that your job is automatically started by the scheduler when you have enough resources are available, and you get the results back. And you may be notified when your job starts or finishes. So, in terms of if it was a service, you couldn't get potentially that huge amount of resources. But since your batch job takes a certain amount of time, it's easier to gather the resources in a batch system. So let's look at a typical HPC cluster. So a typical HPC cluster is accessible from the internet via the login nodes. There's usually an internal network to manage all the nodes, and a really fast InfiniBand network to have the nodes communicate with each other, both for storage and for running parallel jobs. And there's different types of nodes. There's usually an administrative node that's used by the system administrators to run the cluster. There's a scheduling node that basically runs the scheduler. This is the node that figures out when your job starts and finishes and does all the coordination. There's also a set of compute nodes. These are the nodes where your job runs on. And then there are file server nodes. So usually clusters have a shared file server, a file system run by the file server nodes. This is what provides all the storage for the cluster. So that's a view of a typical cluster. Okay, so let's go beyond this. So what are the goals of scheduling? Well, there's basically three goals. The first one is that we want to fairly give the resources to the users according to our policy. So this may not mean that we give everybody equal access. A large group may have more resources than a smaller group. A second goal is efficiency, utilization, and throughput. Basically, we want all the resources to be employed. So when CFI, Canadian government, buys these machines, they want to see them used. They want to see every core used, every single bit of memory used all the time. as well as GPUs and all the other resources. And third, we want to minimize turnaround time. So, your time to the answers, time till your simulation runs. Now, there's a few things important to know about this. All these three things, they're contradictory. Trying to do one basically means that we have to have less of the others. So let's go into it here. Fairness and policy. So as I said earlier, it does not mean everybody gets the same access. An important science project may get a larger allocation, and the scheduler allocates according to the policy. In the efficiency, utilization, and throughput, we want all the resources: CPUs, GPUs, memory, disk, software licenses, bandwidth, and more to be used 100% all the time. Now, obviously, there's going to be gaps between scheduling in these jobs because we won't necessarily have the jobs with the correct ratio of CPUs to memory so that we can fill up all the CPUs and memory, for instance, at the same time. Not to mention disk, software licenses, bandwidth, and everything else. And of course, minimizing turnaround time. So you want to get your results back as fast as possible, especially for iterative users. So if you run a simulation and you need to get the result of that to submit the second job to run another simulation, it doesn't matter if the system is used 100% efficiency if it takes you 6 months for each of those steps. It's not going to make, it's not going to forward your science very much. So for iterative users, it's really important to minimize turnaround time. So we'll get to some insights here. So there's something called wall time. Wall time is the maximum time of your job can run before being killed. And the shorter the wall time, the better we can meet all three goals of the scheduling. So the shorter the wall time, that means that efficiency. It's easier to efficiently schedule small jobs. Turnaround time is better because shorter jobs mean that more resources will be coming available all the time. And the system will be more fair, more responsive to the priorities that was originally set up because the jobs are shorter. So the corollary is that jobs that use a large amount of resources per job result in a reduction of fairness, efficiency, and responsiveness of the whole scheduling system. And the more nodes we have, the better we can meet these goals. So a large, giant cluster, because it has so many nodes, is going to be more responsive. Because even if the jobs are the same size and there's twice as many of them, a cluster that is twice as large will be more responsive because more of those jobs will be ending at the same time. So it's also going to be more, fair because more jobs will be ending all the time. You're going to have a more fair chance at getting resources available on that system. And it's going to be able to be more efficient because there'll be more jobs and more resources, and therefore more opportunity to minimize the holes between. So larger clusters are more fair, more efficient, and more responsive just by being larger. Now, larger clusters are also capable of running larger jobs, expanding capability. But if larger jobs are run exclusively, we lose the advantages of the large cluster. Or we lose the advantages of the more fairness, more efficiency, more responsiveness. What does this mean? Shared resources, such as WestGrid, are better and are used more efficiently than multiple smaller clusters. The larger the scope of shared resources, the better. So a work group cluster will be better than your individual machine. A departmental cluster will be better than your work group cluster. A big university cluster will be better than the departmental cluster. And if you could get national level resources, they're going to be more fair and more efficient simultaneously. So this is the advantage of running on something like WestGrid Compute Canada. It's both more effective and also a better, more effective use of money by the government. So let's visualize a single node. Here is a single node cluster. We see here that it has 4 cores. Today's date is now, if you see it there at the beginning. And we look into the future, day 1, 2, 3, 4, 5, 6, 7. So in this cluster, there's only a single node with 4 cores. This would be an example of a much older cluster than what is typically running on WestGrid, but it's actually easy to illustrate this with a simpler example. So typically on a cluster, there's going to be running jobs. And typically, the scheduling system is not going to kill running jobs. Once jobs start running, they'll have to end, or they have to run out of wall time, and then the system will end them automatically. So typically, the jobs will not be killed, right, by the scheduling system until they run out of wall time. That means that in this cluster right now, there are no cores available. No matter what your priority is, it's going to take a fraction of a day for at least 1 core to become available here in this example. And that's also what happens in real clusters. Okay, so let's schedule jobs into this cluster. So here we have 6 jobs. We've actually sized them. So this is a 4-core job. Job number 1 is a 4-core job that takes 3 days. Job number 2 is a 1-core job that takes 3 days. Job number 3 is a 2-core job that takes 3 days, and so on. So we can actually see the shape of the jobs reflects how much resources that it requires. And let's schedule the jobs in order of priority. In this case, job number 1, we set as to have the highest priority. Job number 2 has the second highest, and so on, with job number 6 being the least highest priority. Now, we'll talk about priority later, how it's determined, and so on, but we'll just assume this priority right now and see how the system works. So the system will try to run the highest priority job in the first instance that it can. Well, that's the first instance that the highest priority job can be run. It's going to start somewhere in the middle of day 4. Why? Because that's the only place it could go. Sure, there's empty cores here, but there's not enough empty cores for that job to run. So in order for this job to fit, it has to wait. Okay, well, let's try to fit the second highest priority job now. Now notice, the second highest priority job will actually run before the highest priority job. Why? Because it requires resources that are available right now. There's no possible way that job 1 will run earlier, and job 2, as you see, is not slowing down job 1 at all. So this is the way it's scheduled. And the same thing happens with job 3. Jobs 4, 5, and 6. So we notice here that job 2 is going to run first, then job 4, then job 3, then 5, then 6, and then only job 1. But all the time, there is no job with a lower priority, with higher priority that's being stopped running earlier by a lower priority job. So sometimes a very high priority job will not be able to run just because of the resources required. Okay, so this is an interesting example. Illustrates a number of things. But let's say that a job finishes early. Let's say a job crashed, or it found its answer and finished early. The job here in yellow is gone. What happens then? Well, these jobs aren't running yet, And the scheduling system cycles every few minutes. So it rearranges the jobs again. It tries to run job 1, and then job 2. Notice that now job 2 is running after job 1. So it's been moved back 4 days, 4.5 days. It was going to start in a few minutes. Now it's going to start 4.5 days later. That's because job 1 can start, and it's the highest priority one. And job 2 cannot delay job 1. Then job 3 is scheduled. Job 4, 5, and 6. Notice that a lot of the positions of the jobs have changed. So are there any questions?
No. No.
Let's look back at our single node cluster. Notice something else. Okay, we have a question. How do we know the state of jobs that are running at the moment? Well, we'll cover this later, but there's commands such as qstat, which will show you how many jobs there are. There's also commands that show you the status of a cluster. So one of those worksheets here is called scheduler command. And if we look through it, there is a whole bunch of commands that you could run and see the status of every job, which ones are queued, which ones are running, and so on. We'll be going through how to read all those commands later. Also, as part of the worksheet we'll be going through, you'll be able to run some of these commands. And to actually get a full understanding of what's going on, it'll actually take you basically all 3 of these sessions until Thursday. Then you'll be able, you have enough knowledge to see everything. So yeah. Another thing, backfill. So there is a command called showbf, and it tells you how many processes are available for immediate use by anybody, no matter what the priority and for how long this is available. This allows you to tailor your jobs to fit perfectly into the gaps left behind by the scheduler. So if you run showbf, you can actually see how many cores are available for how long. So in this case, in Lattice, there's 296 cores on 37 different nodes that could be used for 3 hours. Now, there's a whole bunch of caveats with it, because the cores may be available, but there maybe not be any RAM or disk or other resources available with those cores. But it does give you some information. And it may allow you to tailor your job to fit perfectly into the gaps left behind by the scheduler. Another idea that you could use is you could fill the jobs with short 0 jobs. So if you look at this cluster here, example, and you see these boxes in yellow, these would be 6-hour-long jobs. So, or maybe a bit shorter, 4-hour-long jobs, I guess, I think, size. But jobs of 4 hours or 6 hours long, they could actually fit into the scheduler. If this was the case in a day and a half, there would be, core number 2 would be sitting empty for, I don't know, 6 or 12 hours here. If you had short jobs that require 1 core, your job would fit into here and it would run on those machines. It doesn't matter what your priority is. Your priority would be the most negative of everybody's on a system. If nobody else wants those resources, if nobody else could use those, and you can, you'll be given those resources. So the idea is to run short serial jobs if you can. It's good for you, and also so the system's more efficient. It's running your jobs in the gaps, so that's happy, and you're not really competing with other resources. And because you'll be running so many of these jobs, because there's so many resources available, your priority will likely be very low, so your jobs are not going to be interfering with other users. You may have a low priority, but your jobs are going to be running all the time. So it's basically a win-win-win. So there's a number of myths here with schedulers. Big one is, if there's a large number of jobs in the queue, my job will not run quickly. Now, this is a really big myth. Most of the time, these jobs belong to users with very low priority because they're running a large number of jobs. Especially if they're running little small jobs, they may get a whole bunch of jobs, a whole bunch of resources, but their priority will be low because they're running so many jobs, right? They have run so many jobs recently. Most of those jobs may not be capable of running, as the number of running jobs per user is also limited. So there's limits. So there could be a lot of jobs in the queue, but those jobs aren't even being considered. So they're going to be considered later when that user's current running jobs will stop. In fact, the cluster may even have empty processes available for immediate use because of this, with jobs still sitting in the queue. So deciding if a cluster is busy by the number of queue jobs does not work. So there's a question. So somebody's asking how priority is set. So priority will be basically covered in the second and third day. So Wednesday, Thursday. Another big myth is it is better not to submit too many jobs at a time so other users can run. And that's a big myth. The scheduling system is more fair and more efficient if you submit your jobs earlier, as long as you don't go over certain limits. So there's a certain amount of RAM and a certain amount of compute that is required to look at to keep the jobs in the job scheduler. So if you ask for a horrendously large number of jobs, that may be problematic. But you can ask for literally multiple thousand jobs, and you will still be fine. You'll be under the limits. And when you do ask for a large number of jobs, it allows the scheduling system to make plans into the future. It allows it to become more efficient. And it's important to note that fairness is ensured by the scheduling system. So you will not be hogging the system if you submit a very large number of jobs. The scheduling system will figure out whose job has the highest priority, and it will be fair to you. And we'll go over exactly how fairness is determined and how it will pick the jobs. But as we saw earlier, if your job is lower priority because you're running a whole bunch of them, you're not going to be affecting other people negatively. Or at least other people which also don't have as many jobs in the queue as you do and haven't run that. So here are some tips. Here's a big one. Make sure that your job can run on the resources available on the cluster. So if you try to run a job that requires 96 gigabytes of RAM on Jasper, and I think Lattice, that job will never run. Why? Because there are no nodes on those clusters that have enough RAM. However, the scheduling system is optimistic. It's optimistic. It thinks, well, maybe you do know what you're doing, and the sysadmin is going to come in and install a whole bunch of high memory nodes, and then your job will run. So it'll put your job in the queue, and it will stay forever in the queue, always hoping that Lattice will be upgraded or Jasper will be upgraded. And that's very unlikely. Another big tip is look at the state of the cluster, your account, and the jobs that are there, and to get that information. So we'll go through how to look at that. But this will give you some information on how to run your jobs properly and what to expect of it. Also, if the cluster is empty, let's say Jasper has crashed, which it has today, and we bring Jasper back up, and it's going to be empty because all the jobs may have tried to run and failed. In such a case, the cluster is empty, you could start running jobs. But there's limits. There's actually limits on the cluster in order for you not to take the entire cluster for the entire maximum wall time. So you're not going to be able to take all 400 and some nodes of Jasper for 3 days. We don't let a single user come in and basically grab everything for that large amount of time. But you might be able to grab every single core on Jasper for the next 6 hours. So if you find such an opportunity, the cluster is empty, try to run shorter jobs. You'll be able to run more. Or at least more will run at the same time. So, and that's also good for everybody because although we don't want the entire cluster to be taken over for what's called 3 days, it may take a few hours for other users to log into the machine and start resubmitting your jobs. The system might as well be full during that time. You won't be competing for those resources later with those same users. Any questions? Okay, let's look at basic job submission. So we've talked a little bit about the theory. Now we're going to go through the practice of how to actually submit your jobs. And we're going to start out with the basic ones. And so even if you do know how to do some of this stuff, I'm going to show you some more productive ways of doing these jobs. So there's all kinds of tricks in here to make you more productive. So submitting a job. If you have a program or a simulation that you wish to run, you need to figure out what are the resource requirements of your jobs. So these requirements include wall time, just the maximum length of time your job will run, the number of CPUs, memory, nodes, GPUs that it will require, and on some systems, the queue that you are submitting to. So the command to submit your jobs is qsub. Now, although qsub allows you to specify your job requirements on the command line, you really should put your requirements in a job script. Now, there's a number of reasons for that. The biggest one is so that you can actually see what you submitted. If you do it on the command line, your job fails. You may not know what you submitted. Other people like us who are asked to look at it may not know. It's much better to put it into a job script file, submit that. So let's look at a typical example of a job script. And here it is. Now, we could go through the basics. The first line sets the shell that is running. Next one says that we want one node with one processor per node. We could also use a proc equals 1. That's the same thing here. Here it's asking one processor and one node. Proc equals 1 will be asking for one processor. The next line says that the wall time is 5 hours. So it doesn't mean that your job will take 5 hours to run. It may crash immediately. It says that your job will take at most 5 hours to run. So with regards to wall time, on most WestGrid systems, you're going to be charged for what you asked for. So if you asked for 5-hour wall time, that's going to be used to evaluate your priority later on. The number of resources and for how long. If your job runs only for a few minutes and ends, you don't want to do that. That actually makes the scheduling system quite inefficient for everybody else. At the same time, you want to have this length of time, long enough time for your job to typically finish. You don't want it to die you don't want the system to kill your job just when it's about to finish. So you need to pick a number that is long enough for your job to run, but not overly long because you're getting charged for it. The next line basically says, well, to email you when the job aborts, begins, and ends. So you want the email when the job enters an error state, when it starts, and when it finishes, or not. Right? You could choose here, and you would put in your email address. With a capital N here. You may also want to give your job a name. Instead of a number, you could sometimes refer to it by name. You'll see it by name in some of the commands if we look at jobs. So what you want to do is you want to cd and then PBSO worker. Now, this is the first. So previous to this, the #PBS, those are scheduler directives. That's information that is sent to the scheduler to start running your job. The next lines here are what your job actually does. Now, you want to cd PBSO worker. This is an environment variable. So for those of you that don't know what an environment variable is, in Unix, there are variables that are set inside your shell, and the scheduling system here sets one. And you want to cd to this one, particular one, because this is the location that your job was submitted from. This is typically what you want to happen. And then here I have sleep 1000. Typically, you would be replacing this with a line running your code, or multiple lines. In this case, sleep is a command that does nothing except waits for however many seconds. So we will be using sleep in some of our examples about running jobs, because this will allow you to see the job that is queued and look at it instead of having it immediately end, because it has finished answering and run all the commands that you said. Just CDing to PBSO worker would take a fraction of a second, and you wouldn't actually see the job in the queue. So basically, there's a table of all these things that we went through. This is the same one as you have in your PBS script file. So I've set it up as a separate resource. You could go through here, and it goes on and on about different PBS scripting commands and environment variables. So we'll be referring back to some of this. Most of this information is inside the scheduling document, but it's much easier to look it up if you have a separate one. The scheduling workshop one is 147 pages long for the presentation over the next 3 days. So it's much easier. And we already went through all this. As you can see here, for one processor, you can request it in either format. It means the same thing. Nodes equals 1, ppn equals 1 is the same thing as prox equals 1. They do mean different things when you ask for more processors. for cores. So one other thing, there's something called interactive jobs. So you can ask for an interactive job to run a program on a cluster and interact with it. Interactive jobs are useful for debugging. Now, to request an interactive job, you basically have to have a #PBS minus capital I. Now, if you wish to use multiple processors in an interactive mode, please contact support at WestGrid, as it's easy to accidentally start processes on nodes which your job has not been assigned to. The parallel program you run must be able to interact with PBS or the torque scheduling system and run your jobs on the correct processors. So you don't want your program running on cores that were assigned to somebody else for two reasons. Well, one, because it's going to interfere with the other person, and two, that other person's jobs are going to interfere with your use of those same processors. So you want to actually run on the cores that were assigned to you. And we'll look at that later. So PBS environment variables. Actually, are there any questions? Okay, PBS environment variables. So there's a number of environment variables. Here on Lattice, you could actually write your environment, all the environment variables that you have, by typing a command called printenv, and it will actually show all the ones that are there. For instance, you could what's it called, echo $user. And in that case, it'll give you your username. So there's a lot of information here about that. There's a lot of information about your account in these environment variables. And when your job starts, PBS will set a whole bunch of environment variables, including job name, array ID, and so on. PBSO workdir, the directory that you submitted your job from. And you could use these environment variables in scripts and commands that you write. So one example of doing that, and you could do this on the command line, is you could do stat -a $user. Oh, sorry, -u user. Yes. That gives you all the jobs that belong to you. In this case, there are none. I could, sorry, -u. I could do the same thing. I could submit a job. We could look at just my jobs. But you could do that, and that worked for everybody. Because $user is whatever your user is. So if you type in this command, it'll work for you. You don't actually have to type in your username. This is how you could use some of these environment variables inside your job. So there's a few examples we'll be using. The biggest one, the most important one, is when your job starts, you're supposed to cd to PBSO workdir. And we'll be going through some of these environment variables. So now we're going to break for practice. So we have a number of questions in the online scheduling worksheet on how to submit your jobs. So you'll be asked to submit jobs. Now, there are answers to these questions already. So in this case, if we look at answer 1, this is basically the answer to the first question. I have given all the answers here in order, because it's very likely that going through this, we're not going to have enough time for everybody to write every single problem. In fact, we probably won't have enough time for most people to write for most problems, to write answers. But you should at least try the first few. Another thing to notice that when I run this, we got outputs. So I run answer q1.pbs multiple times. You just saw the last one. When I submitted the job, it gave me a job ID, and it came out with answers and error messages. So the last job ID was 414337, and it created a file called E with job script name and then E414337. This is the file with all the errors in it, and there are none. Here we see the output, and the output is basically, of that command, is basically the host name of the node that it ran on. In this case, the host name is CN005. This is the output of your script that run. So we can rerun that again. And you see if we got a job ID, 414340. And when it finishes, we'll have another one of these answer q1.pbs.e files and .o file. So if you start the first few questions, the first 5. So we'll be going through the first 5 questions right now. After a little while, I'll show what the examples should be, how it should look, and so on, and we'll continue. So right now, you should be trying to submit your first serial job. And if there are any questions, we could go through this. Oh, so somebody asked, what is the file name with the questions in it? The file name is the WestGrid 2016 online scheduling worksheet. There's a PDF and the doc file. And you can also get that information online if you follow the link that I put into the group chat. Now, unfortunately, because these talks are so short, we're not going to have enough time to actually have everybody go through all these questions. So yes, unfortunately, job info is not available on Lattice. So job info is a script that was written by Martin Siegert, actually from Simon Fraser University, and it has been installed on a number of WestGrid machines, but not Lattice. It allows you. It's basically a combination of a lot of other commands. But you could get all that same information using the other commands, if a little bit messier. You will notice that you have to edit the answers with your email address in order for it to actually email you. Because the example, of course, can't have your email in it. So, unfortunately, I'm going to actually have to explain these answers now, and we'll have to go on. Because this is such a short time period, maybe as part of your homework, you'll actually run some of these scripts yourself, create them yourself. but I'm going to explain to you what the output should be. So in here, you should change it to your email address. So the other thing is that we're going to be generating a lot of these output files.
Okay, so,
I included a number of scripts here in with the question.tar bundle. One of those scripts was clean. Basically, it just removes all those job outputs. There's going to be a lot of those as we go through. So, in question, oh yes. So here we can see that the job has completed. And here's the show Q minus U. Yes, so when you see the job that still appears in QStat, in show Q, this is because the job is, but it has already finished. When you do a QStat, you will see a little S here. This is the state. In this case, the C is for complete. It will be like that for a few minutes, maybe 15 minutes, and then it'll just disappear. So you could see Q jobs. So if we do QStat, these are the jobs right now on Lattice. We see some that are complete, some are in state running, some are in state queued, and then there's a few other states that we'll discuss later. But you'll see completed jobs, like for instance this one right here, by one of our users here in the workshop, as well as running ones. Unfortunately, job info is not here on Lattice, so you can ignore that part. In a lot of these commands, I'm going to get you to run multiple commands just to see how the difference is. If we actually look in, I have a run info. It basically runs show Q minus U user, QStat minus A minus U user, QStat minus T minus U user, in job info. So I put it in here so I don't have to type in all those commands multiple times all the time. But it gives you first the show Q minus U output, then the QStat minus A output, and so on. And then it fails trying to give you the job info minus J output. So let's start with the second job. Here, we're asking for a job that asks for one core, emails you when it starts, ends, and aborts, has a maximum wall time of 2 minutes, runs the hostname command, and then runs a non-existent command called hello, so something that doesn't exist, an error. Okay. So basically, answer q2.pbs does this. So asks for one node, has a wall time of 2 minutes, sends the email up, sleeps 30 seconds, runs hostname, and then runs hello, which doesn't exist. We could see that the job is queued. Now it's running. It'll take a few seconds to finish. If you have any questions, please speak up or type it in the group chat. And here we see that the job has finished.
I'm the client, man. I have to get up with you guys.
Oh, there we go. It's taken a few seconds, but now it created files. If we look at the output files, we'll see now that there is something in the that there is something in the error file as well as in the output file. So there's an error line, and it says command hello not found, because there is one. We expected that there will be an error here. So this is how you would get an error if your simulation, there's an error in your simulation. It's going to be written out here. So this example shows you what happens if there's an error in your job. Notice that the correct output, the hostname stuff, still showed up in the regular output. So you have both here, the regular output and the error output. So that's important to know. Also, if you receive an email, you would get notification of what happened there as well. So in the third example, we submit one serial job. It's also supposed to email you when it starts and it aborts. Has a maximum wall time of 2 minutes and sleeps for 200 seconds. Now think about what this is going to happen. We're asking for it to have a maximum wall time of 2 minutes or 120 seconds, and we're asking the command sleep to run for 200 seconds. So obviously, the command sleep may not have enough time to finish. So here it is. As we can see, sleep for 200 seconds, wall time 2 minutes. Now, in 2 minutes, when this finishes, you're going to see what happens when you run out of wall time. In this case, it would be great if you actually set the email properly, because it would also email you this information as well. So we see that this job has now been running for 12 seconds.
Okay.
So you could also be following along with my examples, running them yourself and looking at them, if you so wish. And I see some of you are.
Oh, 2014.
So are there any questions? So it's almost 2 minutes. As you see here, your job actually has been running for more than 2 minutes now. Now there's a tiny bit of grace period, a few seconds, maybe a minute, that you are going to be given before your job is actually going to be killed. And there, it's killed. You see, it's in state C, which means complete. Now we have to wait a few seconds on Lattice, I guess, in order to get the output files. They take a few seconds to get copied over on this machine. And then they are. There they are. So in this case, there's actually nothing here. On Jasper, you would get something in the error file stating that your job was killed because it's been waiting too long. It's run out of wall time. Your email that was sent out should also say that. So it will say how long your job has been running, that it's run out of wall time and was killed because of that. So this is why it's important to have enough wall time for your jobs to run. Unfortunately, I haven't really tested all the questions here on Lattice. But some scheduling systems are running slightly different versions of this. So on some of the WestGrid machines, we're running slightly different versions of the scheduling system software. But here, the result is a bit different. You don't have the error file with saying you run out of wall time. So on Lattice, it would be a really good idea for you to make sure that the job actually emails you when it errors out or finishes. Unfortunately, I didn't set this job to email me. But you should be able to look at your email if you run that job. Well, if you run the job after you edit it with your email address, and you'll see the result about what type of email you would receive when your job dies because it ran out of wall time. So in our fourth example, it's pretty much the same thing as our other examples, except in this case, we're going to give our job a name. In this case, my fourth job. Basically, we give it by typing in that line. That will give you your job's email. Sorry, your job's name. Now, if we look at the output of our commands after we submitted it, we see that my fourth job actually has a different name. In the QStat output, you see the job name, not the script I was started with. So in a lot of these commands, if you want to see your job name in the output, you could set it. Sometimes useful for organizing your jobs. So now we're going to come up to our big interactive job. So in here, we're going to run a job that asks for a serial core, one core, has a maximum wall time of 20 minutes, emails you when it's aborted, before it runs and after it ends, is named my first interactive job, and is interactive. And once it starts running, we're going to be asked to run a whole bunch of stuff. Okay? So basically, here is the PBS script. One core, wall time of 20 minutes, is interactive, has this name, and emails you. And all it runs, well, all I have here is hostname. By the way, notice which directory you are in right now when you do this. Submit the job. Right now, it's waiting for to basically start. It's looking for resources to actually start. As you notice here, my prompt has changed. So right now, I'm on node CN006. I am right now inside the job. So this is what your job script actually sees. So if we look from another place and do a wrong window. If we do if we run our commands, we'll see that we're running, and we have 19 minutes and 13 seconds left over in our wall time. We'll see how long we've been running in the QStat -A -U. So we are inside the job, and now we could start asking our questions. So the first question was, let's look at our environment. Well, we could run printf command and get the whole environment, but that includes everything, all the stuff that used to be there, as well as the new stuff. But if we just grep for PBS, we could see all the environment variables that were set by the scheduling system. Also notice Where are we? We are right now in my home directory. This is not where I started my job from. I started my job from home Kamil capital workshop. But notice that PBSO worker is that directory. So what you're usually told is to cd PBSO worker as the first command inside your job. This is the reason. We probably want to be inside the same directory that we submitted the job from. So we can do that just like the first line of most jobs says you're supposed to do. Okay, we're here. Okay, so let's look at the other things. Well, what is the job's name? Well, we could run this. We call PBS job name. My first interactive job. Or we could just look at the environment variables when we printed them here. It should be along them here. There we go. It's one of these here. Oh, there it is. Same thing with PBS job ID. We could just look it up. There it is. Which directory are we in? So we notice that we used to be in /home. And also path. So path is the variable that contains all your executables. If you try to run some command, you actually have to give you the full path to run it, or it has to be in one of these directories. There's also a question, what does PBS stand for? PBS is Portable Batch System. Okay. So for advanced Unix users, we'll look at something interesting. So Unix has a way of keeping jobs from stepping in, or processes from stepping in on each other. And unfortunately, Lattice does not use it. If you did run this on Jasper, you'd see that there's something called a CPU set, and it basically is a list of processors and memory that your job can touch. So basically, if your job is assigned to run on a couple processors and it wants to run more, it's not going to be let out. At the same time, other people's jobs will be prevented from stomping on your job. And the advanced option here was to look at that. Unfortunately, that's on Jasper, not on Lattice. So let's look at part E. The current interactive job uses only one process, but for future comparison, we're going to run a few more of these. So there's
Yeah, so the WebEx experience you have, not that.
there's a PBS node file. It's going to contain line for every single core that was assigned or processor that was assigned and which machine it's assigned for. The idea here is to look at that. PBS num nodes is going to tell you on how many nodes does your job run at, and so on. So yeah, basically, if you run answers Q5 run in job, that's a script that actually run these. We could look at the PBS nodes file. How many nodes does it run? It's only on one. How many processors? This job only has using one. How many processors per node? The answer is also one. And what is the array ID of this job? There is no array ID. So these questions, you're going to compare it to parallel jobs. You're going to run the same questions inside a parallel interactive job later, or at least we will. So we already showed how this job looked from the outside. And in order to end your interactive session, you type Control and D. At this point, my job has finished, and I'm back. If I do a qstat -a -u mail, type that correctly, it shows that my job is complete. So, are there any questions? Okay. We're going to go a little bit further now. So, types of parallelism. So, we're going to start running using more resources. So what types of parallelism are there? Well, one type of parallelism is to use many serial jobs. So many one-core jobs. That's a great type of parallelism. Another one is to use message passing. Okay, oh, sorry. We have a question. I don't understand why the job switched my working directory from lattice to CN008. So the job did not switch your directory from lattice to CN008. It switched your node. So lattice is a login node, and CN008 is a compute node. So basically, when you went interactive, you became the job, right? Your shell was the job. Stuff that you executed was inside that job. So it changed you onto that node. It did change your working directory back to your home directory, right? Which is why usually jobs have to have a PPSO work there. Is that understood? Okay. Any other questions before we continue? Okay. So let's start on parallelism. So one way of using a lot of resources is just to run many jobs. Another way is to run a job that uses many processors. that communicates between the processors by sending messages on the network. So that's a message passing type job. It's called MPI usually. It uses many nodes. It can run on many nodes, but usually one core per task of that job, per process. These cores can be on the same node, but can be on many different nodes. Single node multi-core job. So this is an OpenMP or Gaussian type job or threaded job. This is a job that usually communicates via passing information inside a system's memory. So in this case, all the cores have to be on the same node. So you do it by passing information inside memory. And a fourth type of parallel job is a hybrid job that basically uses nodes and CPUs. So that's a hybrid type job. Okay. So let's visualize a multi-node cluster. So in order to look at the differences in these jobs, we're going to have a cluster. We're going to have multiple nodes, 3 nodes. And in blue are running jobs. So node 1 was just like the ones we had previously. And we have 2 other nodes.
Make it 10:30.
Are there any questions?
Yeah, oh yeah. Okay, sounds good. Thanks. Yeah, go ahead.
Okay, so let's look at many serial jobs. So here's an example of running many serial jobs. Notice that the jobs are independent. There's 4 of them. Each of them are 4-day long. And they start whenever they could be fit in, just like totally independent jobs were previously. They can run on multiple nodes, but multiple ones of those can run on the same node. So many serial jobs. There's 1 CPU per job. These are the easiest and most efficient to schedule. Also, there's excellent scaling and a linear speed up. What that means is that if you run 100 different jobs, you're going to get, simultaneously, you're going to get 100 times more the usage through the system. And because each of these jobs will be just as efficient as the first one, you're going to get linear speed up. So you're not going to lose any performance due to communication overhead. So example jobs would be a parameter search. In your PBS file, when asked for a serial job in the following ways. You ask for nodes equals 1, ppn equals 1, or prox equals 1. So we see the same example. Serial jobs, we've already run 1. We could run many at the same time. So tips for running more serial jobs. Submit shorter serial jobs. Many shorter serial jobs will run before a large serial job. Checkpoint longer jobs and submit them as shorter jobs. So checkpointing is basically when you have your job write out its state, and then end, and then have another job come in and read the state and restart from the point where it used to be. So This will also save you, this backing up your job will also save you if the cluster suffers hardware or a power failure. Also, it's possible that you want basically 3 months of runtime. There's a good chance that the cluster will fail. Even on the single machine in WestGrid that will actually allow you to run for that long, which is bugaboo. Different clusters have a different maximum wall time. As we stated earlier, the shorter the maximum wall time is, the more efficient and fair a cluster is. So it's all a trade-off between allowing everybody to run longer jobs, because some jobs cannot be checkpointed, and efficiency and fairness. But checkpointing is a good thing. If you can checkpoint, please do so. And here is a great thing, a job array. So jobs arrays are used when you need to submit a large number of jobs with the same job script. Say you want to do a parameter search, you have a whole bunch of different parameters. You want to run the simulation with different parameters put into it. You probably don't want to name each of these things individually. You probably want the whole parameter sweep to have a name and just look at the individual components of it. So there's a naming convention for jobs in an array, which is useful if you don't want to remember a large number of unique job IDs. This is how it would look like, whatever the job name is, and then the square brackets around the number. So jobs arrays are preferred as they don't require as much computation by the scheduling system to schedule, as they're evaluated as a group instead of individually. So basically, a job array, all the jobs in the array are the same. So if you ask for a job array of 100 jobs, they're going to ask for the same amount of RAM and the same amount of CPUs. Because they have the same shape in this Tetris-like game of scheduling, the scheduling system only has to try to schedule each of those jobs once. It doesn't have to do it for all 100 jobs in the array. It just has to say, well, if one didn't fit, the other 100 won't fit. Or if one did fit, the other 100 would fit. So here's how you request a job array. You have a -t and then a range. 0 to 99 would have an array of jobs numbered from 0 to 99. You can also give them individual indexes, 1, 2, 3, 5, 7. Also, sometimes if your jobs, for instance, are very hard on the file system and you want to limit the number of jobs that run, you could do that with %, and then put a number of jobs that a maximum can run at the same time. Now, in order to see the information about your jobs in C shell or TC shell, you may need to have double quotes. And when you run qstat, you may want to do a qstat -t. That will actually show you your job information. If you do a qstat -a, you won't see the information about each individual task. You're just going to see information about the whole job array itself. So here is a sample job array script. We ask for one processor, but we ask for 10 of these jobs in this array. And then we output some information here. Here we output the job name, job ID, but there's also now an array ID. So this is how you would submit many 0 jobs of the same type. So a question, how does the name of the input file is changed in the job array? So actually, our question 10 example shows an example of reading a file with one line of input for each job in the array and starting a job with those numbers. So we'll go through that in question 10 in the examples. So moving on to another type of job is an MPI job. So here we see an MPI job. Notice that it starts at the same time. We have to wait until there's 4 cores 4 processes are available somewhere on the cluster. All parts of the job have to start at the same time. So we see the 4 parts starting. Notice that it's not as efficient as having 0 jobs, because then many 0 jobs could be starting sooner, right? There's holes left behind. So MPI jobs use network for message passing. Each job uses multiple CPUs, each of which can be on a different node. Each process uses different memory space. And it's more difficult to write MPI code than OpenMP, as deadlocks are common. So basically, you can end up in a situation which is called a deadlock. So part 1 could be waiting for part 2, which could be waiting for information from part 3, which could be waiting for information from part 4, which could be waiting for information for part 1. So your job could deadlock. Every single part of your job could be waiting on somebody else who is already waiting on somebody else, some other part. So you have to be very careful in your programming to make sure that your jobs don't deadlock. That's the difficulty of programming MPI-type jobs. But the advantage is that MPI can scale higher than OpenMP, as clusters are typically larger than even large shared memory machines. So for instance, the Jasper cluster has 400 cores. Potentially, you could run an MPI job on cluster that uses much more. Compute Canada is building a very large machine called LP, or is going to be building a very large machine called LP, that you may be able to run jobs that use many thousands of cores. Oh, somebody asked, is Jasper just the login name, node name? Yes, Jasper is basically just the login node name, but we also tend to name the clusters after the login node name. So when we say Jasper, we refer to the login node name as well as the whole cluster. And yes, Lattice is a totally different cluster. So Lattice is both a separate cluster and a separate login node to the Lattice cluster. And you could look at all the WestGrid clusters on the WestGrid webpage. There's Jasper and Lattice and Parallel and Grex and Orsines and Bugaboo and more. Those are the big ones. Oh, and Hungary, which is a very large machine. So MPI job submission. This type of job can have its processes running on any node. Multiple processors can run on a single node. And we submit jobs with #PPS-L prox equals 64. Now, it's possible for you to submit this job with nodes equals 8, processors per node equals 8. It would also give you those, but that's less flexible. In our example here, if we asked for different things, if we asked for all 4 of those processors to be run at the same time, it couldn't start on the same node. It couldn't start here. It would have to wait later in day 2 until enough resources were available. So prox, submitting jobs with prox is better on most clusters. Yeah. The advantage of submitting MPI jobs with nodes equals, say, 10, processors per node equals 12, is that there's faster communication between processors on the same node than processors to the outside. So are there any questions? Okay. So let's go for the next type of parallelism, single node multi-core jobs. So this is the type of OpenMP, Gaussian, or threaded job. In this case, since the communication happens through memory, all the cores have to be at the same time. So notice that this job is starting even later. These jobs in blue were exactly the same for all our examples. And we see that if we have to request an entire node to be all empty, it's going to take us longer to get it. So here we ask for this resource of nodes equals 1, processors per node equals 4. So single node multi-core job. All the threads must run on a single node. The threads share a single memory address space. So the advantage is that you can compile serial and parallel executables from the same source code if you're using OpenMP. And OpenMP is one of the easiest methods of parallel programming and can be done incrementally. So if you have a C program or a Fortran program, you could parallelize the section of the program that is using the most resources, and you'll get a big payoff. You don't have to actually parallelize everything. Of course, you're limited by the parts of the program that you haven't parallelized. So you don't get a speed up during those parts for using multiple cores. So OpenMP job submission. This type of job must have its thread running on one node. All its threads or its processors sharing the same memory. So communication is done via memory. We ask for instance nodes equals 1, ppn equals 8. You can also ask the program to run a number of threads via environment variable. So typically when you're running an OpenMP job, you set an environment variable called ONT num threads. When you set that up, the job running knows how many cores to use. Now, what you usually do is you set ONT num threads to equals to #PBS num ppn or #PBS underscore NP. In this case, you're basically telling OpenMP to run as many threads as the scheduler has given you. In this case, if you write this line in your script, you could actually change the number of cores to the scheduling system, and it will automatically set your job to use the correct number of cores when you're running it. So you probably want to do this. So some tips for running OpenMP jobs. Check the state of the cluster to see if your job will run quickly. If you need to run a larger job, try using Breezy or Hungabee. So those are clusters with more cores per node. In fact, Hungabee has 2,048 cores on its single node. Also, if you have a large number of OpenMP-style jobs, you should consider running longer jobs using less CPUs per job. So it's faster and more efficient to schedule single or smaller processor jobs, but this advice may not apply when you need other resources like large amounts of RAM. Any questions? Okay, a hybrid job. So a hybrid job could ask for, nodes equals 2, ppn equals 2. Or any combination of nodes equals x, ppn equals y. So why would you use a hybrid job? Well, as mentioned earlier, you get, somebody asked, does Hungabee also have large memory? Yes, Hungabee has a very large number of memory. Hungabee has 16 terabytes of RAM. Okay, so going back to why use hybrid job. So one idea of using a hybrid job is that, or at least this type of request, is that you get faster communication between processors on the same node than any processors inside the cluster. So also, it's possible to combine OpenMP and MPI for running on large clusters of SMP machines. you also may need more memory or other resources than is available per core. Also, now this is really advanced, there's advanced systems of running parallel jobs that can utilize resources more efficiently. So communication between cores is faster than between distant nodes. These systems include chapel language as well as partitioned global address space languages, such as Unified Parallel C and Core Fortran. So if your simulation is written in one of those languages, you will often be trying to run one of these advanced hybrid type jobs with this advanced parallel system. And basically here we have all the new PBS commands we've learned. And now we're going to break for practice. Unfortunately, it's already 3 o'clock. So we're going to have to go pretty quickly through these examples. I don't think we're going to have a chance, for you to run these. You could run these while I'm showing the outputs. So let's create a job array that asks for 12 tasks. It's called my job array. So here's an example. It asks for 12 cores. Notice that it has the job array when you submit it. Let's look at the output of all the different commands when you run this. So when you do show queue minus u user, we could see that there's 2 cores that are running, or there's 2, tasks that are running of this job array. There's more that are eligible and a few that are blocked until the other jobs starting to run. If we did a straight qstat minus a, would we just see this like this, with state queued. But if we do a qstat minus t, we can actually see each of these tasks individually. So we could see that some of them have already started running, but the rest are queued. We can redo that. We could see more jobs that are running with show queue. And here we see more states. So some are already complete, others are still running. So in here, we're running 12 separate jobs. Also, in these examples, we're getting a lot more output. Right? Because each of these has both output and error files. We can see different job array IDs are running on different nodes. So the array ID of 1 was running on node 5, but task 2 was running on node 4. So this is the simplest example of job array. Let's look at question 7. Yeah, so okay, we have a question. How does one make different tasks do different things? So you should only make them do slightly different things, right? If they're really different, then they're different jobs, right? If they require a different amount of resources. If you're trying to input different variables in your parameter suite, that will be shown in the answer to question 10, which is, we'll get there in a few minutes. In question 7, we're asked only to run 2 at the same time. So basically, we have %2. And we look at run info. Well, when we look at the q_-t user, we'll see that a lot of these jobs are in state held because they're waiting for the first 2 jobs to start. So we see the first 2 starting, the other ones are still waiting. A few seconds. We'll see that these will end, and the next set of 2 will begin. Now we see 1 job in exit state. And the second set are queued. They're waiting. Probably somebody's running right now, which is why my jobs are still waiting. Oh, and then we see my job start. Task 3 and 4 are starting. We also see that we get a lot of output. Okay. Let's move on to point 8. We could look for jobs with different indexes. So you don't have to just do 1 to 12. You could give the job indexes 1, 2, 7, and -13. In this case, -13 used to be turned into a 13. Now this should give you an error. Finally, the scheduling system actually finds this as an error now. So here we're asking for the different array indexes for your job array. So in this case, we're running, this job is called myArray job 3. It has different indexes. It's 1, 2, 7, and 13. As you can see here, our new job here, the indexes are 1, 2, 7, and 13. So actually, with the version of the scheduler on Lattice, it actually turned the negative index. It ignored it. It just turned it into a positive number. If you run this job with the new scheduler.
No, 13 is minus.
Yes. Yeah.
No, in the script.
Oh.
You didn't have a minus.
Oh, okay. Sorry. In my script, I didn't have a -13. I think I did that because otherwise it would fail on what's it called, Jasper. I'm not sure how it would result with this version of scheduler on Lattice. I should probably change my notes with the question. But as we see here, we could set different indexes. So if you have a variable that you want to, you could pass it via the index. Okay. Question 9. So we're going to ask for a job array that has 2 tasks with indexes of 1 and 4, with 1 core per task, is named myArray job 4, and that prints a whole bunch of environment variables. So on Jasper, for a while, you used to be able to actually run this interactively, which makes no sense at all. Now the scheduler doesn't allow you to do that anymore. But we just wanted to print out all this information. So here's how we would do it. We're asking for array indexes 1 and 4, and then printing out all this information. So here our job is still queued. Now part 1 is running. And now it's done. So here's basically our output. Now we asked to look at the environment variables, so we printed them off. We asked to give a list of node names where the job runs. So basically we printed off the PBS nodes file. Just right here. If we went inside that job, we printed out that file, it would actually give us that result. How many nodes does this job run on one? How many processors does it run on one? So this is what's it called, PBS num nodes, PBS num, PPN, and so on. We're printing off these results. Right. Basically running this. So, yeah. Okay, so question 10. Now, question 10 is a fairly advanced example. It's an example of how an array job would be used by a sophisticated user. Basically, we're asked to run an array job that has 4 tasks, 1 processor each, equals u when it's complete. And we have an input file called input.q10.pbs. And basically, it has a number of it has some numbers in it. And basically, what we want to do is we want to do some math on those numbers. So, can everybody see that? Maybe I'll just cut it. To make it black and white and more visible for everybody. Basically, what this file does is it takes the output of the input file, so that's the input file, which has just 2 columns of numbers, and it grabs a line, it sets the variable line to the number, the line that corresponds to the number, the array ID of the job. So if you have an input file of 4 lines, you start an array of 4. It takes the task number and gives you that line. So this line, that's what it does. It basically uses commands called head and tail to give you the correct line. There's other commands called cut, which will actually give you which field, and we can set field 1, field 2. So this is how you would get the correct line and the correct field that corresponds to the array ID of the job. So in this case, when we run this job, each of these, each of these tasks will get their own line of input. Then they'll set F1 to the first column of that input and F2 to the second column. Then they'll do some math. Basically, they'll multiply the first column number by 2 and add the second column. And it'll set the output. So this is an example of making a task do different things. Now, you could modify this to have many different outputs, but basically, it will run a simulation on this column of numbers. If you know how to do it for one, you can use this example to create an array of jobs. Are there any questions? So we see our job running, even the last task is now completing. Okay. And here's basically the output. So we look at array ID 1. Its line of input is 1 and 11, so it grabs the correct line, correct field, does a little bit of math. The second one, the second array ID, does the same thing on the second line, and so on. So this is an example of how you would make a task do, or an array inside a task inside an array do different things. Is that a satisfactory answer? So this is, a more complex thing for users that, tend to use Unix, and they're trying to be more sophisticated about how they're running their jobs and more productive. Okay. So let's start with an MPI jobs. Yeah. So yes, somebody says they could see how this could be used for running Monte Carlo simulations. So yes, that would be the most typical use of this. So let's start with question 11, which is running an MPI job. So we'll start running a job. We have a start.mpi job, so we can submit that.
I manually just recording notes in the percentage defining that. It doesn't matter. Why in SMC it always no, there's no difference. This is the concept. Yeah, I know. I able to do it a few times. Just not. Remember, SMC now. So this thing can't do it. This is because you were starting.
So we have our job running. Notice how long it took. So our example of our MPI job, it basically runs an MPI command. So it starts with one processor, does an MPI run of the script. And notice that you have to load a module. Actually, this may not work properly here because this example was made to run on Jasper. So it's loading the appropriate module for Jasper. I'm not sure. So there's something called modules, which load the appropriate environment. The names of modules here are different than they are on Jasper. So I'm not sure whether this would run properly. The example here, we would be increasing the number of processors used for this job and noticing how much quicker it runs. So here's an example of running an MPI job. an actual practical example. And we could vary the number of procs that it uses and how long it takes to run. So this is a fairly simple example of running an MPI job. Unfortunately, we really can't do question 11 because, yeah, we're running on Lattice. So question 12 we can do. It's basically asking for us to run an interactive job, or at least we could do most of question 12.
Yeah. Okay.
Let's clean up some of these. So this is basically our question 12.pbs. We do a -I in this case. And as we see here, after I submitted it, it took a while, and now we're inside node 4, which is interesting.
Oh, see, I told you. Yeah, that's why we're here. Because that's all hard drive, like I said before.
Yeah, thank you.
Why? The one gone, one gone, one gone. I don't know. HVAC, that's good.
So we could see all of our PBS environment variables. Notice that there's differences. PBS num and p, PBS NP, sorry, PBS NP, PBS num, PPN are all both 4. So this job has 4 cores in it. If we go back to the work directory, we could. I've actually made what's it called, job 12 executable because it looks for this information. So we could actually get all this information out of there. We could get the PBS job ID, the PBS num nodes is 1, so we're running on 1 node, but the number of processors is 4. The number of processors per node is 4. If we need a list of where each process ID that this job is running, as we see, it's running on those 4 cores. What is the array ID of my job? It has none. And unfortunately, Lattice doesn't have any CPU settings. So this is how a job sees from the inside of a MPI type job. So basically, MPI knows that it needs to look at the PBS nodes file and starts the correct number of processors. That's how MPI job knows how many resources to use. It's because of these environment variables that are set. And we can actually look at this job from another window. And we see that we have 1 node with 4 tasks, 4 cores. And we can Control D or exit. We can type in exit, or we can press Control D. And we quit this job.
Maybe this is not bringing back SSD.
So
Concentrate on that.
we can look at our second interactive job. So it's asked for 4 processors. Again. Actually, we've gone through basically. Actually, no. We'll submit it. So we're going to show you one other thing. So when we submit this job, we'll take this job ID, and we'll run the command called check job. So we'll look at more information later, and there's a lot of very interesting information about your job in the check job command. So you can tell what state it's in, who the user is, when it was submitted, and so on. But here's the really interesting things. So for this question, we have 4 tasks. We have 1 processor per task with almost 3 gigs of memory per task. It's all allocated on a single node. 4 cores are allocated on this node. So you could tell where your nodes are running, where your jobs are running, and how many nodes are allocated, and so on, with the check job command. Question 14, we're going to start an OpenMP job. And we'll look at the same results. It's basically an interactive OpenMP job. So I've been informed we're somewhat over time, quite a bit. So yeah, we can continue to going through some of these examples. Tomorrow's class is basically going to be how to deal with memory. So you're probably going to want to be there at least for the first half of tomorrow's class. For any user, because dealing with memory can be quite tricky. At that point, you're going to be able to submit basic jobs. Maybe we should leave some of these examples for homework for you to run. The answers are all already here. I would suggest you keep going through these questions until you hit question 16 in advance of tomorrow's session. In the scheduling talk, we're going to talk about memory, which will be very, very useful for you guys. And the day after tomorrow, we're going to be talking about the cluster, how it works, how to see if there's any problems, and so on. Oh, and how priority works, and how to set up your jobs to get the most priority and to get the most runs in that you can.